Hello everyone, I am back again for another video. We are in Big Idea 3. We're talking about Essential Knowledge B, which is going to be talking about acids and bases. I'm going to jump off to the side so you can pause the video and you can write down our simple acid and base notes. Alright, here I go. Alright, hopefully that was enough time for you. We're going to be talking about acids versus bases. Now, acid and base neutralization reactions, or when an acid and a base react together, it's one of the most beautiful parts of chemistry because the acid and the base completely annihilate each other, or the two come together and they're left with essentially just pure water. So it's kind of a fun little thing. Let's talk about acids first. Acids are called proton donors, so we're going to see the term proton donor a lot. And when we're talking about a proton, we're talking about an H+ ion. So we're talking about a hydrogen ion, and it's lost its electron. So we take a hydrogen, if we get rid of its electron, all that's left is a proton. Because if you'll remember, hydrogen is atomic number 1, so it's got one proton and one electron, and that's it. And if we get rid of the electron, it's just a proton. So H+ is kind of the workforce of the acid. When we say things are acidic, we're saying that they have H+, or they donate H+ to the solution. So, since they donate H+, and since H+ is just a proton, we say they are proton donors. So acids are anything that will donate an H+ to a solution. Therefore, they have to have hydrogen in them. Okay? They have to have a hydrogen atom in them for them to give up. Now, most acids are pretty easy to spot, because they start with H's. So for example, HCl, H2SO4, those are kind of easy to see. And most of the time acids are written with the H first, just so it's kind of easy for us to see that it's an acid. An exception to that is a pretty common exception, unfortunately. It's acetic acid. Alright, CH3COOH, this is acetic acid or vinegar. The hydrogen is put last. I don't know quite why that one is different than the others, just that it is. Now if we jump over to our other side, we have our bases. Now, our bases are the opposite of an acid. So if an acid donates a proton, then a base has to accept it. So a base is anything that accepts a proton. It's a proton acceptor. Acids are proton donors. Bases are proton acceptors. Now, way back when, they originally thought that bases had to have an OH in them to be a base, to accept that proton. So like sodium hydroxide, potassium hydroxide, because one of the original neutralization reactions was H from the acid plus the OH from the base would yield water. So that was the very first neutralization. We'll see that in a second. However, it turns out that that's not necessarily true. There's something called Bronsted-Lowry bases. Bronsted-Lowry bases are bases that don't have to have an OH. An example of that would be ammonia right here, NH3. NH3 can accept the proton. So NH3 doesn't have an OH present. It'll accept the proton and turn into NH4. Now we're going to worry about this, these names a little bit later, but NH3 is our base, and NH4 is our conjugate acid. So our base accepts the proton, and it turns into the conjugate form of it, or the conjugate acid. And we'll get into bases and conjugate acids a little bit more in class, because they're a little bit easier to see hands-on when we do things. Alright, so let me erase some of these things. Let's talk about how acids and bases dissociate, or how they dissolve in water, and then we'll be done. A nice quick video. Ooh, that blue did not come off well at all. Did not use blue again. Wow, that's going to be fun. Okay. Well, then I guess I'll do my dissociations over on this side here. So, excuse me. So when an acid or a base dissociate in water, they're breaking apart. So for example, let's say I have H2O. This is called dissociation, sorry. This is called dissociation. Let's say I have HCl. Okay, so that's my acid, HCl, hydrochloric acid. When I add that to water, what's going to happen is this HCl is actually considered an ionic bond because the electrons are held so tightly by chlorine and so weakly by hydrogen. Hydrogen essentially never has the electrons. They're always on chlorine. This is essentially an ionic bond between two nonmetals. All right, it's that whole idea that some bonds are ionic and some are covalent, and there's this spectrum in between. It's not two categories, but it's a spectrum. All right, and this falls on more of the ionic side. So what happens is this hydrogen is actually going to come off. It's going to dissolve in water because ionic substances dissolve in water. And this hydrogen is going to leave. And since we said that electron is almost never around that hydrogen, when it leaves, it's not going to take that electron with it. Well, we just said a couple minutes ago that a hydrogen without an electron is a proton. So what's going to happen is this hydrogen, this proton, is going to leave. It's actually going to bond with the water. And it's going to form something called a hydronium. Hydronium is H3O+. When we think of acids doing anything, when an acid does anything, it's really the hydronium doing the thing. Because when we put HCl in water, HCl doesn't exist as soon as water hits it. All right, HCl does not exist in an aqueous solution. What's really existing in that aqueous solution is this. So we can't say, oh, HCl is dissolving the metal. It's not, because HCl doesn't exist in the aqueous solution. What's doing all the work is right here, my hydronium. Okay, my hydronium. That's really what's doing the work. Okay? Now, we could also write this, let's say we didn't want to muddy it up with the water. We could say that HCl just breaks apart into H plus and Cl minus. Once in a while you'll see that. That's more of the simplified form. It's still correct, just not as correct. So this would be more of a first-year chemistry thing where we talk about how HCl breaks apart. This is more of an AP level where we talk about HCl just doesn't break apart. It actually bonds with the water to form hydronium. Okay, now that is an acid dissociation. Now, when bases dissociate, it's not very tricky at all. Okay, so when a base dissociates, let's say we have NaOH. All right, that is a standard dissociation where it's just going to break apart. All right, it doesn't actually interact with the water at all. Okay, so it's just going to break apart like that. Now, let's talk about a simple, let's talk about it if it's not an OH, like this, okay? So this is, it's called an Arrhenius base, but it's a base with an OH. Let's bring back our friend NH3. Now let's say NH3 reacts, or dissociates. Well, you're going to see that there's really nothing to break apart here, right? This is a covalent bond. It's, you know, it's not ionic in any way like HCl, and it's not a polyatomic, right? Like, see how that's a polyatomic hydroxide? It's not a polyatomic like this, and that's an ionic anyway, so that'd be an ionic. But it's covalent, so it's a little more complicated. This one does react with the water. So up here we had what's called an Arrhenius base. An Arrhenius base has just an OH. Arrhenius, for the guy who discovered acid bases, old guy. Arrhenius, so an Arrhenius base is anything with an OH, and that just breaks apart. But here, this is a little bit different. This is NH3. This is called a Bronsted-Lowry. Now, the names aren't crazy important at all, but, you know, some people, it helps them remember with the name. So this is called an Arrhenius base. This is called a Bronsted-Lowry. The guy, I think, was from the Netherlands or whatever, so he has that little weird, like, slashy through the O. I don't know. It's probably pronounced like Brunstead. But anyway, that's going to react with water. And when that reacts with water, we said that this was a proton acceptor. We said NH3 accepts the protons. Well, what it's going to do is it's actually going to not just accept a proton, it's going to take one off of the H2O. And it's going to form NH4 plus an OH minus. So it's going to take my H2O, and it's going to take an H and bring it over there. So I'm going to be left with NH4, 3 here plus 1, NH4, and the OH that's left over. Okay, so what's really happening is the Bronsted-Lowry is taking the hydrogen from it, causing an OH to form. Okay, so we'll talk much, much more about it. One last thing we do need to talk about is water, H2O. here's the thing. Water is both a proton acceptor and a proton donor. So water is both an acid and a base. It's not that it's neither, it's that it's both. Okay, so it will accept a proton. It will accept a proton and become H3O plus. While at the same token, it will donate a proton and become OH minus. So it's both an acid and a base at the same time. And that's why we say water has a pH of 7. All right, a pH of 7 is exactly in between an acid and a base. And it's 7 because it's both an acid and a base at the same time. It depends if it's going to accept or donate. Okay, so hopefully that cleared some things up. We are just scratching the surface on acid-base reactions and things like that, so don't freak out too much, and I will see you guys later.